Imagine a place where time itself bends, where gravity is king, and the very fabric of existence is warped into an abyss. This isn't fantasy. It's the breathtaking reality revealed by the most powerful theories of our universe. This is the realm of black holes, white holes, and wormholes, cosmic enigmas that invite us on an extraordinary journey into the very heart of spacetime. Our guide on this journey is Alex, a young astrophysicist whose eyes, though often fixed on equations and data, held the same boundless wonder as any ancient mariner gazing at uncharted seas. Alex wasn't just studying the cosmos, he was yearning to understand its deepest secrets. He often found himself under a canopy of stars, contemplating the vastness, not as an empty void, but as a dynamic, living entity teeming with wonders far beyond our immediate grasp. He recalled the classic image of a black hole, a cosmic vacuum cleaner, mercilessly sucking everything into oblivion. But the true science, the elegance of Einstein's universe, was far more nuanced, far more beautiful, and infinitely more mind-bending. Alex pictured a solitary probe tumbling towards the event horizon of a supermassive black hole. From our distant, external vantage point, we'd see the probe appear to slow down, its descent freezing in a cosmic ballet against the backdrop of eternity. Its light, stretched beyond recognition by the immense gravity, would redshift into oblivion, fading from sight as if gently erased by the universe itself. A disappearing act, a cosmic sleight of hand, played out on the grandest stage imaginable. This wasn't just a thought experiment. This was the profound truth unveiled by a single, visionary mind, Albert Einstein. His theory of general relativity didn't just describe gravity, it redefined it. It was no longer a mysterious force pulling objects together across empty space, as Isaac Newton had envisioned. Instead, Einstein revealed gravity as the elegant curvature of spacetime itself, a cosmic tapestry woven by the presence of mass and energy. Think of a bowling ball placed on a stretched rubber sheet. It creates a dip, and marbles rolling nearby are drawn into that dip, not by an invisible force, but by the deformation of the sheet. The universe, Einstein showed us, operates on a similarly grand, yet infinitely more complex principle. Alex had spent countless hours wrestling with Einstein's field equations. A complex set of 10 differential equations that beautifully, yet intimidatingly, described this fairy relationship. They were the universe's own blueprint, dictating precisely how matter and energy sculpted the spacetime around them, and in turn, how that curved spacetime dictated the motion of everything within it, from planets orbiting stars to the very paths of light itself. These equations were more than just mathematics. They were a language, allowing us to converse with the cosmos, to decipher its most profound messages. He'd visualized these concepts with spacetime diagrams, those elegant light cones that map out the boundaries of influence, showing what events can affect us and what events we can ever hope to observe. They are the geographical maps of causality itself, illustrating how our past, present, and future are inextricably linked, yet also limited by the universal speed limit of light. They paint a picture of a universe where time and space aren't separate entities, but two facets of the same fundamental reality. The first triumph of these equations, the very first exact solution, came from Carl Schwarzschild in 1916, just months after Einstein published his theory. It was a solution for the space-time around a static, spherically symmetric mass, and it was revolutionary. It predicted something so extreme, so utterly bizarre, that even Einstein himself initially struggled to accept it. The existence of an event horizon and a singularity. The event horizon, the point of no return, a boundary from which nothing, not even light, could escape. And the singularity, the mysterious heart, the point of infinite density, where the known laws of physics break down. These cosmic behemoths, black holes, weren't just theoretical constructs. They are the ultimate, inevitable fate of massive stars. Those celestial furnaces, having exhausted their nuclear fuel, can no longer support themselves against their own immense gravity. Te Koyaps, crushing past the forces that hold up white dwarfs and neutron stars. There is no known force strong enough to resist this inexorable gravitational collapse. The star implodes, shrinking to an infinitesimal point, leaving behind only its immense gravity and the space-time it has warped beyond recognition. Now, but freezing at the event horizon. That vanishing act, for an external observer, is a fascinating effect of our perspective, a quirk of how we choose to describe the universe from our distant, safe vantage point. For someone actually falling into a black hole, there would be no dramatic pause, no sudden jolt, no cosmic stop sign. They would simply cross that invisible boundary, the event horizon, without even noticing anything unusual. Their local experience would remain perfectly normal, at least for a while. That is, until the tidal forces began their relentless work, stretching and tearing them apart in a process famously known as spaghettification. But the crossing itself, utterly unremarkable from their perspective. A vivid analogy that helps demystify this is the space-time waterfall model. Imagine space itself as a river, flowing ever faster towards a colossal cosmic drain. Outside the event horizon, the river flows, but a determined swimmer could still paddle upstream and escape. But once you cross the event horizon, the river of space is flowing faster than you can possibly swim, faster than even light can travel. There's no escaping. You are irrevocably carried towards the singularity, swept away by the current of space-time itself. It's not that objects are pulled through space. It's that space itself is pulling them, rushing them headlong into the abyss. And what about that singularity? It isn't merely a point in space, a tiny dot you could avoid if you maneuvered just right. More advanced tools like Penrose diagrams reveal a deeper truth. The singularity within a black hole isn't a location, but a moment in time. It's the ultimate future, an inescapable endpoint for anything that crosses the event horizon. Much like how tomorrow's an inescapable future for all of us, no matter where we are. Once inside, all paths lead to that singular, final moment. Alex closed his eyes, the vastness of the cosmos pressing him. Not weak fear, but with an overwhelming sense of wonder. The black hole, once a symbol of absolute destruction, was now a profound testament to the universe's intricate design and the boundless capacity of the human mind to comprehend it. But this was only the beginning of the story. If black holes were cosmic drains, what about their theoretical opposites? What other bizarre connections might Einstein's equations secretly harbor? The journey into the heart of space-time had just begun, and the universe, Alex knew, held even stranger, more mind-bending secrets yet to be unveiled. Thanks for watching, and if you enjoyed this journey, be sure to subscribe for more cosmic adventures. Ever wondered what lies at the heart of a black hole? Or if you could really travel through a wormhole to another galaxy? Today, we're diving deep into the true science of black holes, white holes, and wormholes, all born from the brilliant mind of Albert Einstein and his theory of general relativity. This isn't science fiction. It's the mind-bending reality of our universe. Let's start our journey at the edge of the abyss, a black hole. Imagine you're watching a spaceship fall towards one. From your safe distance, you'd see something strange. The ship would appear to slow down, get redder, and then just freeze at the edge. The event horizon, fading away like a cosmic ghost. But is it really frozen? Not at all. For the unlucky astronaut inside, the passage across this point of no return is smooth, completely unnoticed. This bizarre visual effect is a consequence of how extreme gravity warps space-time itself. Light from the falling ship has to climb out of such a deep gravitational well that it loses energy. Its wavelength gets stretched, and time itself appears to slow to a crawl for us, the outside observers. To truly grasp this, we have to ditch our old ideas about gravity. Newton saw it as a mysterious force pulling objects together, but Einstein gave us a revolutionary new picture. Gravity isn't a force. It's the curvature of space-time. Imagine a bowling ball on a trampoline. It creates a dip, and marbles rolling nearby will curve towards it. That's what mass and energy do to the fabric of the universe. This isn't just a metaphor. Einstein's field equations, a set of complex mathematical rules, precisely describe this cosmic dance between matter and the geometry of space and time. The very first solution to these equations, found by Carl Schwarzschild, gave us the black hole. It predicted a boundary, the event horizon, from which nothing, not even light, can escape. And at the center, a singularity. Not a tiny point in space, but an inevitable moment in the future for anything that falls in. Think of it like this. Once you're inside, all possible paths, all future timelines, lead directly to the center. There is no turning back. So how are these cosmic monsters born? They are the dramatic end of the most massive stars in the universe. When a star at least 20 times more massive than our sun runs out of nuclear fuel, its furnace goes out. Gravity, which had been held at bay for millions of years, suddenly wins. The star collapses under its own immense weight, crushing itself past all known limits of matter, past the point where even atoms can exist, forming an object so dense its gravity traps light itself. A powerful way to visualize this is the space-time waterfall. Imagine space itself as a river flowing into the black hole. Far away, the current is slow, but as you get closer to the event horizon, the river of space flows faster and faster. At the event horizon itself, space is flowing inwards at the speed of light. Inside, it flows even faster. That's why you can't escape. It's like trying to swim against a waterfall that's moving faster than you can possibly swim. You are simply carried along by the flow of space itself. Now, what if we reverse the clock on a black hole? Mathematically, Einstein's equations allow for a time-reversed solution. A white hole, instead of pulling everything in, a white hole would violently spit everything out. Nothing could ever enter it. It's a fascinating idea, a cosmic fountain of matter and energy. The problem? We've never seen one. While black holes are everywhere, shaping galaxies, white holes seem to be purely theoretical, mathematical ghosts that don't appear in our real, observable universe. But the theory didn't stop there. By extending these mathematical solutions, physicists discovered even stranger possibilities. The models for rotating black holes, known as Kerr black holes, suggested you could, in theory, avoid the singularity. Instead of a point, the singularity becomes a ring. And if you could navigate through the center of that ring, the equations hinted you might emerge. Somewhere else, perhaps, in a parallel universe, or even an anti-universe where gravity pushes things apart. This led to the most famous concept of all, the wormhole, also known as an Einstein-Rosen bridge, a theoretical tunnel through space-time, a cosmic shortcut connecting to distant points in our universe, or even connecting our universe to another one entirely. Sounds amazing, right? The gateway to the stars. But here's the ultimate cosmic catch. To keep a wormhole open, to make it stable and traversable so a spaceship could actually pass through, you'd need something that, as far as we know, doesn't exist. You'd need exotic matter. This isn't just some rare element. It's matter with negative mass and negative energy. It would have anti-gravity, pushing space-time apart, instead of pulling it together. Think of it as the stuff you'd need to prop open the throat of the wormhole and stop it from collapsing into a singularity the instant it forms. We've seen tiny, fleeting hints of negative energy in the quantum world, but creating and stabilizing enough of it to hold open a tunnel through the cosmos that remains deep in the realm of impossibility. For now. So, are these just mathematical fairy tales? Beautiful equations with no connection to reality? Maybe. But let's not forget, for decades, black holes themselves were considered nothing more than a weird mathematical quirk of Einstein's theory. Many scientists, including Einstein himself, didn't believe they could actually exist. And yet today, we have pictures of them. We detect the gravitational waves from their collisions. They are real, and they are spectacular. This is the true power of science. It's not just about finding the answers we expect. It's about pushing the boundaries of what's known, asking what if, and daring to explore the consequences, even when they seem impossible. The quest to understand wormholes, even if it fails, forces us to probe the deepest nature of energy, gravity, and the very fabric of reality. It pushes us to search for a new, more complete theory of quantum gravity that might one day unite Einstein's universe with the strange rules of the quantum realm. What we've explored today is more than just physics. It's a story about human curiosity. We looked into the abyss of a black hole where time seems to stop. We imagined a universe woven from space-time, bent and shaped by stars and galaxies. We dreamed of cosmic shortcuts and gateways to other worlds. These ideas expand our minds and show us that the universe is infinitely more complex, more bizarre, and more wonderful than we can possibly imagine. Every impossible in science is just a signpost, pointing us toward a deeper understanding. The journey that Einstein began over a century ago is far from over. It continues in the mind of every scientist and every person who looks up at the night sky and wonders. The universe is waiting. Thank you so much for joining me on this cosmic journey. If you enjoyed this exploration into the deepest secrets of our universe, please hit that like button and subscribe for more adventures into the amazing world of science. See you next time. We've peered into the abyss of black holes, these cosmic drains where space-time itself comes to an end. But what if the cosmic film could be what if there's an opposite to a black hole? This very question leads us to one of the most bizarre concepts in theoretical physics: the white hole. Imagine a place in the universe that's the perfect mirror image of a black hole. Nothing can ever fall into it, but matter and energy are constantly, violently erupting from it. It's a cosmic fountain, a one-way exit from some unknown place. Mathematically, white holes are perfectly valid solutions to Einstein's equations. They exist on paper, a beautiful testament to the symmetry of physics. However, there's a big catch. We've never, ever seen one. The conditions needed for a white hole to form, like a universe that's perfectly symmetrical in time, just don't seem to match our reality. So, for now, they remain a profound what if, a ghost in the mathematical machine, pushing us to ask why some things are possible in theory, but not in practice. But the rabbit hole of general relativity goes much, much deeper. The very same equations that describe black holes, when you push them to their absolute limits, hint at something truly mind-bending: connections to other universes. The math suggests that a black hole isn't just an isolated prison in our cosmos, but could be a gateway, not just a shortcut to another place in our universe, but a bridge to an entirely different reality, a parallel universe. This idea, once purely the domain of science fiction, is actually embedded in the fabric of Einstein's theory. It's a humbling thought that the greatest scientific mind of his time might have accidentally written a recipe for interuniversal travel. This leads us directly to the famous concept of wormholes, or as they were first called, Einstein-Rosen bridges. Picture our universe as a giant sheet of paper. To get from one point to another, we have to travel across the surface. But what if you could fold the paper, bringing two very distant points right next to each other, and then punch a hole through them? That sort could then tunnel through the fabric of space-time itself. Einstein and his colleague Nathan Rosen were the first to describe this possibility. It was a direct, tantalizing consequence of general relativity. The problem was, these first wormholes were fantastically unstable. They would pinch off and collapse faster than even a beam of light could get through. Trying to cross one would be like sprinting across a bridge that disintegrates the instant your foot touches it. They were mathematical curiosities, not cosmic highways. But they changed everything. They showed us that space-time isn't just a static background. It's a dynamic, bendable, foldable fabric. So far, we've mostly talked about simple, non-rotating black holes. But in the real universe, almost everything spins. Stars spin. Galaxies spin, and so when a massive star collapses, it forms a rotating black hole, and these are a whole different beast. The first person to solve the equations for a rotating black hole was a physicist named Roy Kerr, and his solution unveiled a structure far more complex and fascinating than anyone imagined. The first thing you'd notice near a rotating black hole is a region called the Erg. It's an area outside the event horizon where spacetime itself is being dragged around by the black hole's spin, like a cosmic whirlpool. Once you're in the ergosphere, you can't stand still. You are forced to move with the rotation. Even if you're traveling at the speed of light against it, you can still escape, but you can't stop the cosmic merry-go-round. Incredibly, theory suggests you could even steal energy from the black hole in this region through something called the Penrose process. A future civilization could literally use a black hole as a power plant. But it gets even weirder. A rotating black hole doesn't have one event horizon. It has two. An outer one and an inner one. And its singularity, that point of infinite density at the center, is not a point at all. It's a ring, a razor-thin circle of infinite density and gravity, spinning at an incredible speed. This is... with a point singularity, your fate as sealed you will be crushed. But with a ring singularity, there's a theoretical loophole. If you could navigate with impossible precision, you could fly right through the center of the ring, avoiding the singularity altogether. So what happens if you do that? What happens if you pass through the ring's singularity of a rotating black hole? This is where the theory takes us to the absolute edge of imagination. The mathematics suggests that by passing through that ring, you wouldn't just be crushed. You might emerge somewhere else entirely. You could pop out in a different part of our own universe, millions of light years away. Or you might emerge in a completely separate, parallel universe. Some solutions even hint at emerging into an anti-universe, or a region where time flows backward. The black hole transforms from an ultimate prison into a potential portal. It's a concept so vast it makes most science fiction look tame. It's a mathematical whisper of a reality that is almost beyond our ability to comprehend. Now, it's time for a reality check. As thrilling as these ideas are white holes, traversable wormholes, gateways to other universes, they all come with major asterisks. The beautiful mathematics that describes them usually assumes a perfect, idealized scenario. For example, they often rely on the concept of an eternal black hole, one that has existed forever in a perfectly empty universe. Our universe is neither eternal nor empty. It's a messy, dynamic place filled with matter, radiation, and the constant forward march of time. When you try to apply these elegant theories to the gritty reality of our cosmos, big problems pop up. The stability of these cosmic tunnels is a huge issue. For instance, the passage through a rotating black hole might be a mathematical possibility, but it's likely to be catastrophically unstable. The slightest disturbance even, a single photon trying to pass through could trigger a storm of infinite energy that would instantly collapse the gateway, destroying anything inside. The bridge is there in theory, but it collapses if you even look at it. But the single biggest hurdle for creating a stable, traversable wormhole is the need for something called exotic matter. To prop a wormhole open and stop it from pinching off, you need a substance with negative energy density. In simple terms, you need matter that has anti-gravity. Instead of pulling space-time inward like normal matter and energy, it would need to push it outward. This isn't just science fiction. It's something that, according to our current understanding of physics, simply cannot exist on a large scale. While quantum mechanics does allow for tiny, fleeting moments of negative energy in specific microscopic situations, it's nowhere near what you'd need to stabilize a tunnel through. It's like trying to build a skyscraper out of soap bubbles. So, where does that leave us? Einstein's equations have given us a stunning canvas of possibilities. They paint pictures of cosmic shortcuts, fountains of creation, and gateways to other realities. Yet, the physical laws of our universe seem to place strict limits on these possibilities. The mathematical beauty often clashes with the hard, energy-constrained reality we live in. Are these concepts just dead ends? Elegant math with no physical counterpart? Or are they clues pointing toward a deeper physics we haven't discovered yet? Perhaps a future theory of quantum gravity will show us how to create exotic matter, or reveal that these cosmic gateways are real after all. For now, the questions themselves are what drive us forward, pushing us from the known into the exhilarating realm of what might be. The universe, it seems, always keeps its most profound secrets close to its heart. Thanks for watching.